This is a joint work by Jiaxun Cui, Hang Qiu, Dian Chen, Peter Stone, and Yu Zhu. Our topic is Coopernaut end-to-end driving with cooperative perception for networked vehicles. This video demonstrates a dangerous scenario where a vehicle is doing aggressive lane change maneuver when its vision is occluded by the slowly moving truck. This dangerous behavior can be mitigated by augmented vision, which motivates our work to seek an end-to-end driving policy that uses multi-vehicle perception. Since line of sight sensing can be occluded, and vehicle-to-vehicle communication with 5G technology allows larger data transmission bandwidth, we hope to learn a condensed representation of the perception of each vehicle and let the controlled vehicle drive based on the joint perception with the connected neighbor vehicles. Before we dive into the Coopernaut, let me introduce AutoCAD SIM, a scalable network augmented driving simulation framework on top of the CALA, with example accident-prone scenarios. Specifically, we consider overtaking, left turn yielding, and red light violation, where occluded vision can cause potential safety concerns, and they are so common in our everyday life. Next, we introduce Coopernaut. It is an end-to-end driving framework which uses LiDAR as input, and the whole pipeline is driven by imitation learning. First, each vehicle encodes a point cloud in their perspective into dense point representations by the point encoder, and then spatially transform and send them as a message to the ego vehicle. All the received messages are aggregated by another block of point transformer in the ego frame. Finally, a control module will decide which action to take based on the joint representations. The supervision of the imitation learning comes from an expert developed in AutoCAD SIM, who has access to the ground truth information, physics sensor data, and the predict plans of all the vehicles. We first train every model using behavior cloning, which simply tries to mimic the expert's action given a fixed set of trajectories, but suffer from distribution shift. Then we apply a dagger algorithm to each model so that they can learn from the new interactions with the environment under the help and the supervision of the expert. All training data are mainly composed of normal driving trajectories, but with a small portion of them are collected under dangerous scenarios. Our quantitative results demonstrate that no V2V sharing models has performed poorly on all tasks, while the 3 cooperative driving models achieves higher success rates and lower collision rates. Our model Coopernaut costs lower bandwidth than the other 2 baselines while maintaining high performance. We also found that Coopernaut can generalize to a variety of traffic densities, consistently outperforming the no V2V sharing baseline. Finally, let me show one qualitative video that depicts how Coopernaut works. In this overtaking scenario, the collider is going the opposite way, but occluded by the truck. Our model waits until the safe clearance appears, while the no V2V sharing model aggressively changes lanes as the past experiences are mainly safe. In summary, our contribution are as follows. We introduced Coopernaut, an end-to-end driving model with cooperative perception via V2V channels. Our model learns compact representations for communication that can be used by the ego vehicle to improve driving decisions. We developed AutoCAD SIM, a network augmented autonomous driving simulation framework to evaluate Coopernaut and baselines in accident-prone scenarios and to promote future research on vision-based cooperative perception. Our results show that Coopernaut substantially reduces safety hazards for line of sight sensing under realistic V2V communication bandwidth. We have more videos on our website, and please check our paper for more detailed discussion about the results. Thank you very much for listening.